right off the bat, notice we are dropping a ball from the top of a building. And you guys live on Earth, so you know what happens when you drop something. Does it just fall at a constant rate?
No.
What happens? So you physics guys are like, oh, it's 9.8. Yeah, great. It speeds up. Does not have the same velocity from start to finish. So we learned yesterday that we could calculate average velocity, but asking how fast the ball is going doesn't really make sense because it's always changing speed. So today, we're not gonna find average. If you look at what we're gonna find the actual velocity at the 1 second mark. We're gonna find the instantaneous velocity, the speed at an exact moment in time. And up until about 300 years ago, you couldn't do that. That's calculus. So I am going to birth, like I said, calculus in front of you. It's a little graphic. So let's read this. It says a ball is dropped from the top of a building. Then it gives you a bunch of sentences about how I came up with the formula, the function there. The function's the important part. It tells me that to solve for d, I can plug in a time and it will tell me how far the ball has fallen. So it says due to the Earth's gravitational pull, the distance d in feet, the ball travels after time t in seconds is given by that function d equals 16t squared. So question, what is the velocity of the ball at the 1 second mark? So we don't know how to do this, but what we do know is how to find average rates of change. So I'm gonna start you off. Let's talk about finding the average velocity over an interval. So I'm gonna start my interval at the 1 second mark. And I gotta look at an interval of time, just like we did on the warm-up. So I'm gonna look at the interval from 1 second to 2 seconds. So that's time 1, the little subscript means time 1, and this is time 2, kind of like my ending time, 2 seconds. And in this interval, now we can talk about everything that's happening. So first, how much time has passed? Well, the calculation is t2 minus t1, which is 2 minus 1, which is 1 second. And yes, I want you to write all of that in that little box. It'll be helpful down the road. So during this interval, 1 second has passed. My starting distance, to get that, I have to plug t1 into the function, which is 16 times 1 squared, which is 16. 16 feet, but we'll be lazy and leave the units off right now. So 16 feet. My ending distance, just as you know, I plug in t2 to the function. So 16 times 2 squared, which 2 squared first because it's order of operations, times 16 is 64. So now my lapsed distance, that's how much distance has changed from the start to the end. And my starting distance was 16, my ending distance was 64. So I'm going to do 64 minus 16, which was, put this underneath, that was d of t2 minus d of t1. That's how I got those values. And I think I get 48. So I have traveled a distance of 48 feet in this 1 second window. Finally, the payoff, the thing we really cared about. This lap speed, we've learned this as average velocity. What was the average velocity during this 1 second period of time? Well, it's the distance we traveled divided by the time it took. So it is just 48 divided by 16, 1, which is 48 feet per second. So we have an average velocity. It doesn't answer my question about what was happening at 1 second, but I know from 1 second to 2 seconds, I was traveling this on average. So here's where we can start to be clever. I chose 1 because that's kind of the point I'm interested in looking at, so I'm gonna choose 1 again. And we're gonna do the process again. Except that 2 didn't have to be a 2. I just chose it to be a 1 second interval. Here's where I can be a little bit clever. I'm gonna make that smaller. I'm gonna make that closer to 1. Let's do something like 1.5. Let's see what's happening during a smaller period of time. and see if we can get an even better average that's closer to what's actually happening in 1 second. So now I'll go through the calculations one more time, and then I'm going to have you guys do it for the next. So, to get the lapse time, it's the ending time minus the starting time. So now we're looking at a half a second window of time. What's happening in this half second window of time? The starting distance. You still are doing exactly what we just did. So it's still going to be 16. We're plugging in the starting time to our function. But now the ending time is going to be a little different. This time it's 16 times 1.5 squared. And this will tell me my ending distance. Anybody have it?
36.
36? Exactly?
Yeah.
Can we get confirmation? 36. It's not that I don't doubt you, Matt. Yeah, it says it on my paper, so I guess you're right. So, 36. So now, lapse distance is my ending distance minus my starting distance. That is 20. Ending distance minus my starting distance. Now the payoff question. What was the average velocity? It is my change in distance divided by my change in time. And that gets me, anybody? 40 feet per second. Okay. So it went down a little bit. That makes sense because I cut off a half second where I was going faster. So now my average from 1 second to 1.5 seconds was 40 feet per second. Here's what I want. Take 30 seconds. You're gonna turn to the person next to you in a minute and tell them what the heck I just did. So be like, I don't understand what Mr. West just did. All right, here's what he did. And see if you can figure out where I'm going with this. Go, 30 seconds, seriously. Make sure you're okay with what I just did and where I'm going. Look good. Go home and relive this day.
I was afraid I was gonna like sneeze, like my nose started tickling. I'm like, don't drop the phone. Don't drop the phone.
It's not a professional video. It's just to remember. All right, time's up. So, anyone, I'll open this one up and then I'll start calling on you. Anyone want to tell me where they think I'm going?
Oh.
So brave. Yeah, Blake, what do you think?
Happens to the velocity the time changes nothing.
So where do you, I mean, we have a lot more spaces. What would make sense to do in the next line? Because you're right, but.
Make the time interval smaller.
Yeah, let's do the interval even smaller. Question, Nick? Or? We're getting to all the acceleration is going to come into play later, but no, we're trying to find the instantaneous velocity. But Blake's right. Let's make the interval even smaller. So this time you're going to do the calculation. So let's go from 1 second to 1.1 seconds. 1/10 of a second interval, and let's find the average velocity there. So go through it, do these calculations. I'll call on a few of you for your answers. We'll see if we're able to do the process for this time frame. And we'll talk about it, see if we start to notice something. See if we start to converge to a value.
If it's starting from
I know you guys are still calculating, but I'm gonna start asking for answers. Cameron, my lapse time, where are you? Where's Cameron? There. How much time has passed?
1/10 of a second.
1/10 of a second has passed. Tiny window of time. Angela, where are you? There you are. What is my starting distance? Still 16. I'm not changing that. It's my ending distance that's gonna change. So, Danae, what is my ending distance? Do you have it?
19.36.
Yep. Can I confirm that?
Yep.
Give me thumbs. All right. 19.36. You said? Cool. So now my lapse distance. Adriana, how much distance have I traveled in this time frame? Just 3.6. I think you got an extra. Yeah, so 3.36. The ending distance minus my starting distance. And now the payoff question. Matt, do you have the average velocity for me?
I do.
What is it?
It is 33.6 feet per second.
33.6?
Yes.
Did anyone carry it longer than it? Is it 33.6 exactly?
It's exactly that.
Okay. I like precise. Good. So, looks like our numbers are getting smaller and smaller and smaller. Let's see if we approach some value. Can we make our interval smaller? Of course, we can always make smaller numbers. What do you want to do? Let's do 1.001. Go! And let's see if we can get an answer to what's happening. I know you're still working, but I'll call on a few. Steven, do you have how much time has passed? 0.001. The tiniest of time frames. 1/1000th of a second. Starting distance. Kenny, do you have the starting distance for me?
16.
Still 16. That hasn't changed. It's the ending distance that changes. Hopefully you plugged 1.001 into the function, not 0.001. We always plug this guy into the function. I'll give you a minute there. Xander, do you have the ending distance?
Yeah.
What is it?
16.032.
Looks good to me. Barely moved it all in this 1/1000th of a second. But as long as we have an interval, we can do an average velocity. No problem there. So, distance traveled. Lapsed distance. Tommy. Tommy, where are you? He's the one that's not here today. Matt. It's right here, the next one. Matt, how much distance have I traveled? 0.032. And finally, the payoff question. What was my average velocity here? Lucas, do you have it? What did you get? Did anyone have it with the decimal still? I want the decimal. 32.016?
Yes.
Okay. Last one that you will do by hand, I promise. If you had to guess, what do you guess the instantaneous velocity is at 1 second? Looking like 32, right? Let's be sure. Let's do one more and then we'll go to the payoff. So do one more for me. Let's do it from 1 to 1.30 with a 1. 1/10,000th of a second will be the lapsed time. And if as long as it's an interval, we can still do average velocity. So I know you're still calculating, but I'll ask. Sam Holden, do you have the starting distance for me? Still 16. Ending distance. This is the one that changes. Hopefully your calculator can handle it. Austin, do you have the ending distance? 16.0032? Yeah. So how much distance have I gone this time? Michael Gordon, do you have the answer to that?
32.00.
So I think it's 0.00. Yeah, 32. Cool. And finally, the one I really care about. Delangela, do you have the lap speed for me?
Hold on, I'm getting there.
Cool. I'll give you a minute.
Hold on.
Did your calculator go funny? Some calculators go to scientific notation. Just check with Jenna, do you have it?
Yes.
32.0016.
32.0016. Okay, now, if you are a betting person, what do you think the instantaneous velocity is at 1 second? You guys have a little more enthusiasm.
32.
It's looking like 32. All right, ready for calculus to be born in front of you? Here we go. I'm gonna do this problem one more time, but I'm gonna be a little more clever. So watch and do this with me. I'm still gonna start it at 1 second. However, look what I'm doing. I'm just making numbers that are very, very, very close to 1. So I'm gonna call this x, and I'm just gonna write a little note to myself that I'll worry about later. X is very close to 1. Very mathematical, I know. But I'm gonna write a little note to myself, being like, all right, this is x, and x is just very, very close to 1. It's a little bit bigger, a tiny bit. But as long as I remember that, I can do everything the same. So now the rest of this is gonna be filled out the exact same way. Everything we did in this first line, we're gonna do the same, but now we're just gonna have an x in the problem instead of a number there. So Nick, first up, how much time has passed? And remember, to find the lapse time, I always did this minus this time minus this time. So any idea how much time has passed in this situation?
1 minus x.
They give-
X minus 1.
There you go. X minus 1. So everything still works. It's just an x minus 1, which maybe you're not comfortable with, but remember, we can worry about x in a little bit. Starting distance. Natalie Windsor, where are you? There you are. What's my starting distance? 16. It's still 16. I'm going to go back to this notation. That was from plugging T1, or I'm just going to put, plugging 1 into my function. So I got that by plugging 1 into the function. And it was 16. How about my ending distance? Isabella, how would I get my ending distance?
So 16 times x squared.
Yeah, so how did you get 16x squared?
Just plug in x.
Plug in x. So really what you're doing is d of x, which is 16x squared. So now, how much distance have I traveled? Johnny, how much distance have I traveled during this time period?
16x squared.
Yeah, so he said 16x squared minus 16. Really, that's just d of x minus d of 1. It's what we got when we plugged in x minus what we got when we plugged in 1. And the payoff question. What is the average velocity? And Megan, where are you? What am I dividing? Do you know what the average velocity would be? Over x minus 1, which is really just d of x minus d of 1 over x minus 1. And you're like, okay, what is this doing? Well, now we got to take care of something. This didn't make a lot of sense. You're like, x is very close to 1. Have we learned anything in this class, maybe over the last 3 weeks? Mathematical way to rephrase this so that it works in this problem. Nandini, you have it?
The limit.
The limit what?
The limit as x approaches. Oh, 1.
Yeah. So that's what the limit does. It's saying instead of using x equals 1, which I can't, as a limit as x approaches 1, if I throw that in front of this guy, you have now discovered, and you can put this under your conclusions, you have now discovered the formula for instantaneous velocity at x equals 1. So this is equal to, and I want you to write it, the instantaneous velocity at x equals 1. Otherwise known as, get ready, this is the first time you're hearing it in this class, the derivative at x equals 1. You'll hear that word probably 50,000 more times this year. There's your first big experience with it. Also, mathematicians hate to have to write words a lot. So you'll see this. Our function was d. So you'll see d primed at 1. That little prime symbol means derivative. So this is saying the derivative of the function at 1, or the instantaneous velocity at 1. So now let's actually go back to the problem and solve it using what we have. We know that it's the limit as x approaches 1. And it was this problem right here, 16x squared minus 16 all over x minus 1. And oh my gosh, does that look like a problem from your last test? Say yes.
Yes.
Have we solved lots of limits? We definitely have. Anyone want to tell me what I need to do? Yeah, you skipped the first step though. Direct substitution?
Doesn't work.
So yeah, directly substitute. And here's my advice: don't be lazy about writing limits. Rewrite it. Let's factor the top. Anyone know how it factors? I'll throw it out there. Sam, what do you have? X plus 1, x minus 1, all over x minus 1. And do we notice something?
Yeah.
Oh my gosh. So really what we have is limit as x approaches 1 of 16 times x plus 1. And when things cancel, we're super happy. And we can direct substitute. And lo and behold, 32 feet per second. Confirmed. Okay. So let's take a minute and step back what we just did. We found the average velocity over an interval, average velocity over a smaller interval, average velocity over a smaller. Then we were very clever and used a limit to say as some value got very close to where we were interested in finding the derivative at, we could set up the definition of the derivative. And then we just did some simple limit calculations, and lo and behold, that popped out at us. So here's what I want to do. On the back of your, if you have room on the front, do it underneath. I think we still have room on the front. If not, you can go to the back. Let's do one more problem. Yeah. Let's find the derivative, or find the instantaneous velocity at a different point. Instantaneous velocity. Let's find it at x equals 3. This is what we're going to be doing a lot tomorrow. Let's find the instantaneous velocity at x equals 3. So we have our formula. It's not going to be 1 this time though. It's going to change. Since we're interested in finding the instantaneous velocity at 3, we got to change everything to, d of x minus d of 3 all over x minus 3. That's the setup. So now we keep our function the same, which was 16x squared or t squared. I'll just keep x's. Minus. Now you plug 3 into the function and get an output. Did anybody do that for me? Someone plug 3 into the function for me. Thank you. All over x minus 3. And that's a top that looks like it wants to be factored. So this becomes this guy. And oh my gosh, it worked again. I'll kind of be lazy here. This is the same as x plus 3, x minus 2. Cancel. I'm left here. And now direct substitution works. You can plug in 3. 16 times 6 is, anybody? 96. You have now found how fast this ball was going at the instant of 3 seconds. So when I drop my ball, 1, 2, 3, take a picture, that's how fast I was going at that second. Okay? Instantaneous velocity, super important, super powerful. One more thing I want you to do today and we'll call it a day. Now you do it all on your own at t equals 2. So now you do this at t equals 2. See if you can get the calculation. All right, go.